too much to disappear. I'm showing, not telling. I feel like yelling so you hear. I'm a mess and I'm anxious, and I just can't bear this, my dear. All of my kindness has led you to blindness, I fear. Take a step back from the ledge that you're standing on. Look down the canyons molded by standing still when I've tried for so long. I can't keep trying so hard. Once in a lifetime, well honey, it's my time to know. My rock now, I'm sinking. I need to be me alone. I'm so sick of the sadness. I need this madness to go. Anchored, not moving. My engines are burning a hole. Take a step back from the ledge that you're standing on. Look down the canyons molded by standing still when I've tried for so long. I can't keep trying so hard. Take a step back from the ledge that you're standing on. Look down the canyons molded by standing still when I've tried for so long. Take a step back from the ledge that you're standing on. Look down the canyons molded by standing still when I've tried for so long. I can't keep trying so hard. I am standing alone, and from here I can see the clouds. I have climbed up so high that I can't seem to get back down. I can't feel anymore. Try to speak, I can't make a sound. I am trying to fight, I can't remember how. Tell me why I can't escape from this broken place. No one seems to win, looking for a way back in, but fighting with myself won't make it work. Fighting with myself won't stop the hurt. I am stuck where I am, ripping at my skin to see what it really is sitting inside me. Tell me, should it be this hard to breathe? I am starting to wish that I gave myself a chance to believe. Tell me why I can't escape from this broken place. No one seems to win, looking for a way back in, but fighting with myself won't make it work. Fighting with myself won't stop the hurt. Fighting with myself won't make it work. Fighting with myself won't stop the hurt. I am standing alone, and from here I can see the clouds.
All right. Welcome back, everybody, for our second episode of what we've taken to calling Audio Hour, although it probably won't be exactly an hour. I'd like to thank the network for bringing me back for a second episode, not canceling me after the pilot. We're going to get through a lot today, a bunch of topics that I'm going to throw at you. I'm warning you now, it's going to be a little fact-heavy, a lot of information, a lot of black and white. But it's all necessary, and it will all inform the creative choices that we'll be making as we go through this. Today we're talking about signal flow and gain and different types of microphones. We're going to start off with signal flow. In essence, audio propagates. It begins somewhere, and then over what can be a really fast path, like from source to your ears hearing it, it starts and ends with you hearing it. Or when we're talking about recording, that path gets a little bit longer and a little bit more convoluted. But this is going to be a discussion of how audio is captured, how it's manipulated, and eventually how it's reproduced and perceived by the listener. The easiest image that I can think of for signal flow is, think of it like water. It has to have a source, and then it flows through its river to wherever it ends up washing out. There's always a start, and there's always an end. There's always an in, there's always an out. So regardless of how complicated the chain gets, if at any point you start losing you're not understanding like how audio is getting to a source, or what a source's role is, just remind yourself to consider, okay, whatever this component is, what's feeding it, like where is it getting its signal, and then where is it sending its signal to, and you should be able to get yourself figured back out from whatever step. Now, I'm going to go ahead and preface this. I wanted to display a diagram of how, like, from a sound source to listener, how audio is recorded and processed. I couldn't find one online that had like the exact components I wanted in the exact order, so I just made one myself. So we all get to enjoy a little laugh at my expense. I had to bribe a couple of my teachers to let me out of kindergarten way back when, and this little example I'm about to throw up is gonna explain why that was. So here is my hand-drawn signal flow diagram. All right, there it is. So, as you can see, starting in the upper left corner, we have a sound source, which could be this crudely drawn guitar. It could be any instrument or voice, anything that creates sound. That sound travels through the air as waves, and then if we're trying to record that sound, we have to put a microphone in the path of those sound waves. The microphone will react, and we'll get into like the actual details of how that reaction occurs later in this segment, but the microphone will react to the sound waves and translate that into electrical energy, whereupon that energy is sent over an XLR cable to a preamp, which we will talk about again later in this segment when we're talking about gain. But the electrical signal of the audio will be sent to a preamp to be amplified to a usable level. And then I put this next stage in asterisks because it is kind of optional, especially for understanding most of us are going to be working almost entirely in the box without any outboard gear. But if you wanted to process any of your sounds with any sort of hardware, it would happen at this stage. But whether that stage is there or not, the next stage is your audio to digital conversion, your AD. The most common way this occurs, especially at the level of someone who is self-recording, usually the preamp and the AD converter are one component called an interface. Interfaces don't always have to have preamps integrated, but most smaller ones will, because the manufacturers of those understand that the people buying them usually aren't working with consoles or any sort of external preamps. But regardless, the preamp stage is still a distinct stage, even if you are using an interface with integrated preamps. The preamp is still dealing with electricity, an analog signal, and then it boosts it before it sends it to its AD converter, where that signal is converted to binary code, and that code is then outputted into a computer, which is where all of your digital signal processing happens. That's where that code is going to be written to a disk so that it can be stored, recorded, and played back later. It goes into whatever DAW you're using so that you can change the sound as needed. You can control relative balances of your sound sources. And then as your mix happens in the computer, in the digital realm, it will then be outputted to a DA converter, a digital to analog converter, which is the same as an AD converter, but in reverse. It's a device which translates the binary code back into electrical information. And again, usually at the consumer level, the interface contains a DA converter as well as an AD converter. That's usually what's denoted by your monitor knob. If any of you are using one such consumer interface, that's referring to the output level of your DA converter. So that DA converter changes the code back into electrical energy, and then that is sent to whatever your playback mechanism is, whether that's speakers, like we talked about last week, whether that's studio monitors or a nice set of over-ear headphones, which I'm going to go ahead and assume that all of you are listening on one of those two things right now. And then that speaker, just like the original sound source, is going to react to that signal and create sound waves, which will then travel through the air to your ears as the listener. So, as you can see, our path begins with a sound source, an instrument, and ends at our perception of it, at our ears. So this is the most basic signal path for recording audio. As you get into mixing, like within the DSP stage, the signal flow can get a little bit more complicated as you're talking about routing, like sending a single source to multiple places in parallel, or stringing together a series of inserts where a sound source feeds like some processing, and the output of that processor feeds the input of another processor in series before it is sent back into the mix. And we can talk about that more when we get into some later episodes and we're talking about your mix layout and things like that. But for right now, this is the best way I can think to shed some light on how the audio recording path usually takes shape. And again, just when in doubt, look for the in and look for the out. And that will always steer you in the right direction. So, with this understanding of signal flow, it now becomes important to recognize that each of these components in this chain have a certain sensitivity, shall we say, and they all are not necessarily the same as one another. For this reason, the preamp stage will most often be used to bring the mic, like the signal that the microphone is outputting, up to a really high level, so that regardless of what component it goes through, the electrical signals will be high enough that whatever device is in the chain will be able to perceive it and process it accurately. Which brings me into our next topic of gain. But before we get into gain itself, I just want to take a quick second to mention the concept of the decibel. The decibel is the standard unit of measure for any sort of audio, but it's important to note that the decibel is it differs from other standards of measurement in that it is a relative value as opposed to objective values. Like an inch is always an inch, a pound is always a pound, regardless of what that value is measuring. The standard unit of measure is the same regardless. A decibel is not like that. A decibel is only useful for measurement relative to some pre-existing value. There are actually tons of different dB values For instance, when we get into microphones a little bit later, we're going to be talking about dBSPL, which stands for sound pressure level. So when we're talking about dBSPL, that's the relative change in sound pressure. So if we say that the hit of a snare drum is 20 dBSPL louder than a guitar amplifier, that just means relative to the sound pressure, meaning the air that it moves, a snare drum moves more air in dB than a guitar amplifier. Another derivation of decibel measurement is dBFS, which stands for decibels full scale, which is used in digital processing or broadcasts where there's a ceiling on the maximum value that any sound source can have, and therefore everything within that is relative to that maximum value. That really only comes into play for our purposes in mastering, which we won't talk about for a good long while yet. The most commonly referred to dB value in mixing and recording is what's called dBu, which stands for decibels unloaded. There's a really electrical engineering heavy explanation as to why it's called that, but suffice it to say that when we're talking about gain, we're talking about decibels unloaded, dBu. But from now on, as that's understood, as I'm discussing relative values, I will only say dB. So just keep that in mind. And I know that's a lot, but it's worth stating at this point. So with that, we can begin our discussion of gain and what that is, how it affects audio, and how it's used. So I have here, this is a digital representation of what's called a channel strip. If we had an analog desk in front of us, the layout of each track would be something similar to this. But the only part of this that we're going to focus on is the very start, and don't let this layout confuse you. This knob right here at the bottom where it says in, this is the preamp of this channel strip. If you were looking at this on an analog board, that would be at the very top. But for sake of space on the screen, they've put it down here. We're going to be concerned with this, and we're also going to be concerned with the last stage of this, which is the fader. And we'll talk about the differences between this knob and this fader as we get into this. So, like we said before, gain that is applied at the preamp stage is used to bring the electrical signal of the microphone to a high enough level that all the other subsequent pieces of the signal chain can accurately perceive that information. It's kind of like, think about it like the first hill on a roller coaster. Like the car has to get enough force off of the first drop from that hill in order to complete its loop around the track of the roller coaster. This is kind of the same way. You want to make sure that you give your sound source enough gain off the microphone that it will be able to carry itself through all the successive portions and components of the signal chain. So with that understanding, there's kind of like an added caveat to that, in that it's not that it takes the exact electrical signal coming out of the microphone and just moves it straight up. Like the electrical signals are fundamentally changed by adding gain. And that's really the difference between gain and volume. Because adding gain does add volume, but adding volume does not always add gain, and we're going to talk about why that is here. The process of electrical amplification will fundamentally change the waveform that's coming into it. It's going to manipulate the amplitude. It's going to impart, depending on the type of preamp used, it's going to impart certain what are called artifacts, which are just ways in which the original electrical representation of the sound form is changed. It's going to add some harmonic distortion in the process of making it louder, which can be a good or a bad thing, again, depending on the preamp and the desired effects that you want from it. There's also what's called a noise floor consideration that you have to take into account when you're adding gain, so that as you give your electrical signal more strength, sometimes it is prone to pick up noise along the way, like just this annoying hum in the background of your audio, which is why like the nicest preamps advertise having the lowest noise floor, meaning you can get your original signal as loud as possible before you start hearing any sort of excess noise within that. Often, in addition to just giving the signal enough strength to make it through the signal chain, preamps are often selected or differentiated from one another because of the way that they fundamentally change the waveform. Certain preamps are said to have certain colors or different characteristics, so engineers will that are experienced with dealing with multiple preamps and have the option of dealing with multiple preamps will often select a specific preamp for a specific sound source because of the way that it will change that sound source's information, supposedly being in a pleasing and distinctive way. Interestingly enough, a lot of engineers have been known to say that they would rather have a really nice preamp with a decent microphone than have a really nice microphone with a decent preamp. Just to give you a sense of how important the gain stage really is when we're talking about recording and the subsequent mixing. Having a really nice preamp or using a preamp in the correct way can really improve your sound quality and your recording and your mixing before you apply any processing at all. So best practices in applying gain to sound sources. And we're going to talk a little bit, this will kind of feed into our discussion of microphone types a little bit later, but in general, like I said, think about it like the hill in a roller coaster, where you want to make sure you have enough for the total length of the route. So in general, you want to give all of your sources enough gain to ensure that without giving them too much. Because if you push it past a certain point, it will begin to distort. And that's a very audible, easy to perceive thing. You'll hear that it starts sounding harsh and sharp and generally not pleasant. But you do generally want to get your sources as close to that point without crossing it as is possible at the preamp stage, because it's always easier to make a source louder after the fact, but it's really difficult to make a source, or I'm sorry, I'm saying that backwards. It's always easier to make a source quieter after the fact than it is to try to make a source louder after the fact. Once something's been committed to tape or committed to computer disk, you will have an easier time in the mix reducing the level of something than increasing the level of something. So you want to make sure that you kind of overestimate on gain, but under no circumstances do you want to cross what's called the clipping point, the point at which the preamp is going to start distorting. You always want to make sure you maintain a healthy distance from that point. If you want to experiment with this, and you have the means to do so, you have a microphone and a preamp, just plug the mic in, speak into it, turn the preamp until your voice no longer sounds like your voice, and just sounds like a harsh, garbled mess, and then back it down from there until it starts to sound like your voice again. It's important to note, too, that you generally, in recording, want to set your gain and then leave it there for the duration of the recording. You don't want to be changing your gain like from song to song or take to take. You want the gain to be consistent throughout. So it's important to note that when you're taking into account the ceiling of that preamp, like the point at which it's going to start distorting, you want to make sure that you've left enough room below that point to account for the loudest that source is going to be playing over the course of that take. So, if it's a snare drum, you want to make sure that drummer hits that drum as hard as he's going to hit it in the song at the loudest point when you're setting your gain, to make sure that you're not going to distort when he gets there. And just speaking from experience, if you've set it at sound check to where he's like, whoever is playing, whoever the musician is on whatever instrument, if you set the gain at sound check to where they're not clipping, it's always a good idea to bring it back down a little bit past that point, because people tend to play louder when they're actually recording, because there's other sounds involved and there's excitement and adrenaline and all that. So just don't make the mistakes that I've made. Let me make those mistakes for you. So just to kind of try to illustrate the audible differences between gain and volume, I'm going to play back some audio here. I've got a set of drum overheads here. They're completely dry. This is just straight off of the recording. Okay, I'm not sure why I got disconnected there, but we're going to keep going for the sake of the recording. Hopefully you have rejoined me. Apologies for getting cut off. But as I was saying, I have a set of drum overheads that are dry, and I'm going to try to illustrate for you the audible differences between adding gain and adding volume, the difference between turning up the preamp or just pushing up the fader. So first I'm going to play you a sample just of the dry audio as it is. So here's that. All right, so that's our dry recording. Using this digital representation of a channel strip, I'm going to simulate a process that would be happening in the analog realm at the level of the preamp. But just for the sake of this example, I'm going to do it in the box, which is not the same. Please don't think that it is, but it can mimic that effect. So again, here's the dry audio. Okay, now I'm going to activate this plugin, and it's going to simulate the effect of turning up the fader by 5 decibels. So here's that. Okay, so you hear how it's effectively the same as what you were hearing before, just louder. Now if I switch over, this is going to simulate the effect of adding the same amount of gain. I know that's a really subtle difference, and I'm going to A-B the two a little bit more closely so you can try to perceive it. But effectively, what it's doing, like I said, as this knob is turned up, that's changing the waveform. Fundamentally, it is turning the original source into something else. It is a representation of what it was before, but it's with additional distortion and harmonic characteristics and amplitude. When this fader is up, it is just affecting the amount of that signal that's being contributed to your mix. So it's the same signal, not changed at all. It's just controlling how loudly it is played back relative to the other signals. So I'm going to toggle between the two. Just watch on the plugin. If this fader is up, then you're listening to volume. If the fader is at normal, like at unity, and this knob is turned to the right, then you're listening to gain. Pay attention to the color of the sound and the placement of the different sounds within the image, within the stereo image, that is to say the left and right. All right, so right now this is volume. And this is gain. Volume. Again, I know it's really subtle. Depending on your monitoring system, you may not be able to perceive it at all. But if you have a decent set of headphones or monitors and you listen really closely, you should be able to detect a difference in the cymbals, specifically first. Here, check it out. So here's volume. And then gain. Hear how it it's tightening them up, quote unquote, or bringing them spatially lower but more forward, like further from the top of your head but closer to your eyes, so to speak. Here, I'll check it out again. Volume. And then check the cymbals. Gain. Also listen to the snare drum difference. Specifically the snare drum's interaction with the cymbals. So here's volume. Listen to the snare relative to the cymbals. And then gain. Notice how that snare comes out a lot more. It gets the snare up on top of the cymbals rather than the cymbals kind of washing over it, as was the case in the original signal. Like, listen to this. Here's the original. As opposed to all right, so yeah, again, thank you for indulging what I know is a very subtle thing to look for, but that was the best way that I could think to kind of demonstrate the difference between adding volume and adding gain. That topic, like all of these topics, is as big and convoluted as you want to make it, but I think for our purposes, that's probably a worthwhile description that we have so far, and we're going to move on to microphone types. Give me one moment. Okay, so first thing to understand about microphones is that they all have what's called a polar pattern or a pickup pattern. There are basically 3 types. Each of these types has derivations that really don't make a ton of a difference, but if you know these 3 main types, that'll get you everywhere you need to go. The first type is what's called omnidirectional, which is here on the left. As you can see, that's represented as a circle. When you're looking at these diagrams, the center of each circle is the microphone. So if you're using a microphone that has an omnidirectional pickup pattern, is going to pick up any sound source anywhere around it in equal measure. It doesn't matter from what direction the sound approaches the microphone will perceive it equally, regardless of if it's in front of it, behind it, above, below. Does not matter. Second pattern, and by far the most common pattern in microphones, is what's called the unidirectional or cardioid. It'll be more often referred to as cardioid because if you look at it on this diagram, it's kind of shaped like a heart. So if you're looking at this center diagram, and your microphone is understood to be the center of that circle, the way that's read is the microphone will pick up the most sounds in front of it, and then it will decrease in its sensitivity to sounds on the sides of it before canceling out any sounds entirely behind it. Cardioids are the most commonly used microphones for what's called close miking in the studio, because they will pick up whatever they're aimed at, essentially, and not pick up whatever is going on around them, which enables you to get a really clean signal so that you'll have an easier time manipulating it in the mix. You won't have to worry about, bleed from other instruments factoring in. The other type, which is less common nowadays, but it's called bidirectional, or more commonly known as figure 8. Looks exactly like how that diagram depicts it. The microphone will pick up everything in front of it and everything behind it, but nothing on the sides. This was used when multi-track recording wasn't really available yet, to create separation of parts. Like, for instance, if there was a duet happening, one singer would be placed on one side of the mic and the other singer would be placed on the other, and that way they would each have like an equal share of the microphone. Or like a bluegrass band in the round would either play around an omnidirectional microphone to pick up everything, or put a figure of 8 mic sideways in between them just to capture kind of like a stereo image of the sound that was coming at it. The first type of microphone, there are three basic types, is a dynamic microphone. A dynamic microphone was the first to be developed historically, is pretty much the simplest design, and the way it works is, so as you can see on the diagram at the left, there are sound waves that hit a diaphragm, which is just any sort of thin material membrane, kind of simulating your eardrum. That diaphragm is in contact with a copper coil, which is suspended over a cylindrical magnet. As the sound waves impact the membrane, they cause the coil to move back and forth over the magnet, and the magnet reads that change in force and converts that to electrical signals, which are carried out by that wire there, which is effectively like the microphone's, if we're going to keep using the ear analogy, that's your tympanic nerve that carries the signals to your brain. That's the wire that's going to carry electrical signals to the XLR cable that carries your microphone signal to all the other components in the signal chain. Dynamic microphones have a lot of variety. Some examples of them are these. In the upper left, you have probably the most common microphone that there is, a Shure SM57. You can kind of even just envision, like, at the end of this, like the membrane, coil, and magnet configuration just existing within that little black bit on the end. really versatile microphone, but commonly used on snare drums, guitar cabinets, and we'll get into why that is here in a minute. Upper middle is a Shure Special 55. It's really good for making vocals sound mediocre and not much else. So don't worry about that one too much. Then there's, in the upper right, an Electro Voice RE20, really good on kick drums and certain voices, particularly really loud or really staccato ones. Lower left, we have a Shure SM7B, which is kind of a frequent counterpart to the Electro Voice RE20, used on similar sources, kick drums, bass cabinets, and certain specific voices. Lower middle, that's a Shure Beta 52, really good on kick drums, really good on bass cabinets. Again, noticing a theme here. Lower right is a Sennheiser MD421, really, really good on toms and really, really good on horns. And then all the way at the right is probably the most recognizable microphone, a Shure SM58, the world standard in vocal microphones. But you noticed the trend in the instruments that these are used on, and here's why that is. Because dynamic microphones have a very specific frequency range. And with that, and because of their construction, they also have a very specific dB SPL handling. Remember, we were talking about sound pressure level before in our discussion of gain. We'll get into that here in a second. So dynamic microphones in general have a pretty narrow frequency pickup. This graph in particular is a frequency pickup graph of a Shure SM57. So you notice that it's not picking up a lot of this low-end information. It really doesn't get full energy until about 200 hertz. And then it's fairly flat for the mid-range. And then at 3000 hertz, it begins slowly boosting before it tapers off at about 10K and then drastically is reduced. So for that reason, because it's not picking up the full frequency image, and because of the really durable construction of the dynamic capsule, dynamic microphones have a really, really high SPL handling, meaning they can capture really, really loud sounds without distorting them. Dynamic microphones can pick up SPL peak levels up to 150 decibels, which is, like, just for some reference, the threshold of pain for most people is 100 decibels. So 50 decibels louder than when something starts to hurt your ears, and it'll still pick that up with fidelity and not distort it. So because of its high SPL handling and its relatively narrow frequency pickup, dynamic mics tend to be used most for drums, you know, because of their loud peak levels, like when the stick hits the drum. Like I said, horns, because, you know, especially brass, where they can just generate massive amounts of volume. Guitar amplifiers for the same reason. And sometimes vocals as well, but usually the vocalist has to be really loud in order to get a good sound out of that. Dynamic mics also have a relatively low impedance. Again, we're not going to get too heavy into the electrical engineering of that, but suffice it to say, the lower the impedance, the more gain a microphone will take in order to get the signal to a usable level. Dynamic microphones have an average impedance of 150 ohms, which compared to other microphones is fairly low, as we'll get into. So that's dynamic microphones. The next type is a condenser. Now, a condenser works essentially, in terms of its construction, it's similar to a dynamic in that there is a membrane, that front plate, usually made of like a metal foil, which will vibrate relative to sound waves. But instead of vibrating over a magnet, it vibrates over a metal plate, which has an electrical current running through it, which is why there's that battery marker at the bottom of the diagram. It's a built-in capacitor in the microphone, which is basically just a big coil of copper that stores electrical energy, which provides a charge to the back plate so that when the foil of the front plate vibrates against it relative to the sound waves, the back plate is able to detect those fluctuations in the electrical voltage, which is then sent out through the wire into your XLR cable and into your signal chain. Condenser microphones kind of look like this. The upper left is a Neumann U87, which is kind of the end-all, be-all of vocal mics. The middle microphone is an AKG C414. Really, really versatile mic, like one of the most versatile mics that exist. Has any number. This mic in particular will cover all of the polar patterns. It will run in omni, in cardioid, and in figure 8. The Neumann U87 will run in cardioid or omni. Forgot to mention about dynamic mics. Dynamic mics are always in cardioid. They are only made in a cardioid pickup pattern. So that is important to note. On your upper right is a Shure Beta 92, most typically used on kick drums. On the lower left here, you have a Neumann KM184, which is what's known as a small diaphragm condenser. If you notice, it's smaller than these other condensers at the top, which are large diaphragm condensers, and those are the two varieties, large diaphragm and small diaphragm. The Neumann KM184 is omnidirectional, also a fairly versatile mic, but not usually used in close miking, usually reserved for room miking or applications where the mic is further away from the sound source, and we'll get into why that is in a bit. Lower middle here is an Earthworks TC20. Like the Neumann small diaphragm, it's omnipolar and also typically used as a room mic. And then at the far right is a Shure Beta 98, which is kind of the condenser equivalent to the Sennheiser MD421 in that it's really good on toms and really good on horns, most typically used on those two sources. Condensers differ themselves predominantly from dynamic mics in that they are said to be active, whereas dynamic mics are passive. When it's said that a mic is active, that means that they require an outside power supply. Some of the older microphones have like a physical power supply that you have to plug into the wall and then plug the microphone into that to run. But nowadays, most commonly, microphones run on what's called phantom power, which is a small amount of voltage that is supplied from your preamp through the XLR cable, which charges that back plate so the mic can work. Because of their construction, condensers are used over dynamics for certain applications because they have a very wide, very flat frequency pickup. This diagram is for the Neumann U87, but you notice that it starts picking up at 40 hertz and is a flat line from 40 hertz to 8,000 hertz. Then there's a slight bump at 10,000 hertz before it starts rolling off. Because of their construction and because of this frequency pickup, they are not able to handle as high of an SPL level as a dynamic microphone. because they are generally more sensitive. They will distort sooner with loud sound sources. Condenser microphones tend to have a max SPL handling of around 115 decibels compared to the Dynamics 150. So for that reason, you don't typically see these as close mics on anything loud like drums or guitar amplifiers or bass cabinets or anything like that. But they are very often, almost always used on lead vocals because vocals tend to not be as loud or as transient peak heavy. They're used as room mics a lot or in tandem with a close mic to give a little bit more space in a recording. Condenser microphones also are of a lower impedance than dynamic microphones, of a higher impedance than dynamic microphones, meaning they will require less gain to achieve the same level of sound output. Remember that dynamic microphones generally have an impedance of 150 ohms. Condensers have an impedance of 250 ohms. And remember that the higher the ohms, the lower the gain required to get the sound. There's one more type of microphone, generally speaking, that is used in recording. There are, more types than this, but not really that are used for our applications. And even these are growing less and less common, but it is, There we go. It is the ribbon microphone. Ribbon microphones are effectively the same thing as dynamic microphones, but instead of having a coil suspended over a magnet, it has a ribbon, like a really thin, super thin strip of metal suspended in between two magnets. The sound source will vibrate the ribbon, and the magnets will read that difference, and then that signal is converted to electricity and sent out. Ribbon microphones, while they are not super common, mostly because they're really hard to make and therefore really expensive, for that reason they're not as common, but they sort of provide kind of a compromise between a dynamic microphone and a condenser microphone, and we'll get into why that is, but here are some examples of what ribbon mics look like. The upper left is an RCA 77, which is kind of like the prototypical ribbon mic. It's one of the few ribbon mics that has multiple pickup patterns. It has all three. It has cardioid, omni, and figure 8. The rest of these microphones only pick up in figure 8, and that kind of makes sense because if you remember the diaphragm, it's a ribbon suspended in between two magnets. The magnets are on the sides, so it's going to vibrate with sound sources relative to the front or the back of it. Upper right is an RCA 44. Lower left is a Coles 4038, and the lower right is a Royer 122. Ribbon mics as a class of microphones are typically only used as room mics or very specific types of vocals. Sometimes you'll see them on acoustic guitars or guitar amplifiers, or as, like perspective mics, like not close mics, but near a drum set as a whole. The reason for that is because they are similar to dynamic mics in construction. They also have a relatively high SPL handling, not as high as dynamics, but compared to a condenser's 115 SPL handling, a ribbon mic will handle about 125 dB SPL. So not quite as high as the 150 of a dynamic, but certainly higher than that of a condenser. So they can handle some louder sound sources than condenser microphones, but where they distinguish themselves from dynamics is in their frequency pickup. Their frequency pickup, this is specifically for the Coles 4038. As you can see, trends as a very flat line and picks up most of the audible frequency spectrum, whereas if you remember, the dynamic frequency chart was pretty narrow and had a significant high-end boost and a significant low-end roll-off. So using a ribbon mic allows you to kind of get a condenser-like frequency pickup, but used on louder sound sources that you would usually use a dynamic for. Ribbon mics are, like dynamic mics, are also passive microphones. Important note, if you ever find yourself in a situation that you are using a ribbon mic, under no circumstances should you ever send phantom power to it. Remember, phantom power is the power that condenser microphones need in order to run. If you send phantom power to a dynamic microphone, that's not a big deal. A dynamic microphone doesn't need it, but it won't hurt it if it's present. But the power in phantom power will hurt the ribbon mechanism in a ribbon microphone. So before you plug in a ribbon microphone, if you're using one, always be sure to double check that phantom power is not enabled for that channel, because it will damage the microphone. I myself do not have any access to ribbon microphones, so I could not include one in the example I'm about to show, but I did record an example here of a sound source that is picking up, that is being picked up by a dynamic microphone and a condenser microphone, just so you can hear the difference of how those microphones perceive sound. So first I'm going to play a dynamic microphone, a Shure SM57, recording an acoustic guitar. That sounds like this. Okay, that's your dynamic pickup, and then the condenser is the same acoustic guitar, same part at the same distance, but recorded with a large diaphragm condenser, specifically a Rode NT2. That sounds like this. So you can hear that the condenser track is decidedly warmer, has a lot more low-end information, and is a little bit darker, meaning it doesn't have the same high-end boost that the dynamic had here. I'll just quickly A/B the two again so you can rehear the difference. So this is the dynamic microphone, and this is the condenser. Listen to the low end. There's significantly more in the condenser than in the dynamic, but you're also getting a more full frequency image. So, and there are upsides to both, like the dynamic perspective. The acoustic would be able to play louder, and you wouldn't have to EQ it as much to get it out of the way of like bass instruments, because it doesn't pick up many of those frequencies anyway. But the condenser would give you more options for EQing it after the fact, because it's just picking up a more accurate frequency spectrum. And it's those sorts of understanding those differences of the microphone classes that will inform your choices in recording, being guided by what you want to do with the source when you go to mix. So, when you're going to select a microphone for a recording, ask yourself, okay, with this part, what do I want to do with it when I go to mix this song? What do I want this part to contribute? What characteristics do I want this part to have? What do I want to be able to do with it after it's been recorded? And that will effectively guide you in selecting, should I use a condenser for this? Should I use a dynamic? How close should I get either of those things to their source? How much gain should I apply to them as I'm recording them? So yeah, I know that's a lot, but that's all I have. I know I've thrown a lot at you all this episode. So again, feel free to get a hold of me if nothing is making sense or need something explained a little bit differently or a little more in depth. Feel free to reach out. Yeah, that's all I have for episode 2. Next week, at the same time and place, hopefully we don't get cut off that time, but next week we'll be talking about editing in a DAW, which is a big topic in itself. But I'll be demonstrating some of the considerations where after you've recorded a part, all the parts in a song, the way that you edit those things before you can start mixing. And there's also going to be a quick discussion about using digital plugins. So yeah, I will leave you with that. Oh, also, homework for next week. And I'm just holding everybody on their honor system that they did their homework last week and critically listened to lots of songs. Homework for this week is try to start thinking about the signal flow model, both in the audio that you're listening to and also just in everyday life, because it's present in lots of things, more so like in addition to just audio, like, in your shower or in your car or, streets, public transit, ingress, egress from buildings. Start to see if you can observe and identify inputs and outputs in your day-to-day life in situations beyond just audio. And I will leave you with that.